Hello, my name is Ethan, and this is my third part for my third project in fluid mechanics. As you can see in the past two videos, I did laminar and turbulent flow, and I walked through them. And in this video, I'm going to be walking through the Inviscid case. It's a little simpler than the other two, but for this case, I'm going to have to do a different mesh, a little more refined mesh. Um, like I said before, in the previous videos, the geometry is the same. So all I'm going to do for geometry is import geometry cylinder wall, and that should be good. And so I'm just going to move on and edit the mesh. Okay, so now that I'm in mesh editing, I'm just going to name all of my lines again, or my edges. Up here, it's symmetry. On the left, it's velocity inlet. On the right, we have a pressure outlet. And in the center, our circle is our cylinder wall. Okay, we're going to do the same basic approach again. So with mesh, we're going to go to method and select the face. And we're going to do triangles and click generate. We have that, but it's very unrefined. So we're going to go to mesh, insert, sizing. I'm going to select this edge. I'm going to go to number of divisions, and I'm going to select 500. And here as well, we're doing hard behavior. And I'm going to click generate. Okay, so now that that's generated, we are also going to add an inflation like last time. I'm going to click the face, and then for boundary, I'll select the edge of the circle. Here we're doing a first layer height of 1 meter, maximum layer height of 150. But unlike the previous two, for the growth rate, we're going to do 1.05. And I'm going to click generate. Okay, so that inflation has loaded in. But again, as you can see, the mesh is pretty unrefined here. So for element size, unlike the other meshes for the previous cases, I'm going to use an element size of 0.12. And I'll click generate. All right, so as you can see, the mesh has loaded in. It's a very, very detailed mesh. Took a really long time to get all generated, but here it is. And that, I believe, is all for the meshing. So I'm just gonna click update. And now I'm gonna go into setup. Once again, double precision and for processors. Okay, so I have my mesh in. All of our general settings seem to be correct. Pressure-based, steady, planar. For our model, I'm gonna change it to Inviscid, viscous Inviscid. Um, for our material, I'm gonna use air, and I'm gonna be using the same density. So I'm not gonna be changing any of that. I'm going to double check that the calculation will use air, and it is. So for our boundary conditions, we have our velocity inlet. And for this, we're going to use 5 meters per second as given by the project. Hit apply and close. I'm going to double check that all of our other conditions are correct. Yeah, pressure looks good. And we shouldn't be able to change anything about the cylinder wall. Um, yep, nothing we can do. So I'm going to go to reference values, compute from the velocity inlet, and all of our values look correct with the 5 meters per second. I'm going to choose surface body for reference zone. And once again, I'm going to go to report definitions, create a new drag report with our drag coefficient. And selecting the cylinder wall. And clicking OK. And for our method, I'm actually going to be using simple and least squares. But for our pressure, we're going to be using Presto. It's a little bit faster of a calculation, and everything else seems to be correct. And so I'm going to go to initialization. I'm going to use 30 iterations. Just going to make sure that that went through. Okay. Yep. I'm going to initialize. And this takes longer because of the larger mesh and more defined mesh. And so now that our initialization is done, I'm going to go to calculation. And once again, I'm going to use 500 iterations. And click calculate. All right, so our calculation is complete. I'm just going to go to our drag coefficient and I'm going to compute that. And for an Inviscid flow, our drag coefficient should be very, very close to 0. So our coefficient of drag of 0.0002 is, sort of represents the theoretical nature of Inviscid flow. I'm going to go to plots, XY plot. This is going to be, once again, a pressure coefficient. And I'll select pressure coefficient along the cylinder wall. I'll plot that. And this also seems to be correct. Going from 1 and, you know, staying across the position of the cylinder wall where 0 is right pointing towards the free stream. This seems to be correct. Or no, I'm sorry, position 0 would be in the behind, in the wake of the cylinder. So that looks correct. And so now I'm going to do my velocity magnitude along the wall, surface wall, and I'll plot that. And this is correct for velocity, where our velocity should reach about 10 times what it is the initial velocity. I believe that's correct. So yeah, that I believe is all for the CFD base. So now I'm going to move on to results. Okay, so now that I'm in CFD post, I'm going to do the same thing that I've done for the past two videos. I'm going to start with a pressure contour and making sure to use symmetry 1, pressure, and 100 contours. And if I zoom in here, as you can see, it's a very uniform distribution of pressure, given, it's in viscid flow. Um, so not much to see here really, but I'm going to go to velocity contours. Making sure I do symmetry 1, velocity U, and 100 contours. And as you can see, it's very evenly distributed. Um, Not much to see really, except when I do turn the, go from the z-axis, you can definitely tell that there is, some interaction with the wake and the cylinder with the flow. So certainly Inviscid, but there's still 5 meters per second of fluid flow affecting, some of the velocity contours. And so finally, I'm going to do the same thing for the streamline. I'm going to go from the velocity inlet. I'm going to do 5,000 points and click apply. And so as you can see, the streamlines are very, very small, but it's Inviscid flow. So not really much to see, but I believe that's it for the project. Thank you.